Today we run Gram-Schmidt twice. Once on ordinary three-dimensional vectors, and once on quadratic polynomials. Same machine, different costumes. The algorithm is not magic. It is just repeated subtraction of projections, followed by normalization. A broom with notation, basically. Start with a linearly independent list V1 through Vn. We build orthogonal pieces called U's. Then normalize them into E's. At step K, remove every component pointing in the directions already built. What survives is perpendicular to the old directions. Very suspiciously useful. Now compute. No hand waving. Humanity suffers but correctly. First, use the standard dot product on R3. We start with 3 independent vectors, because using a broken list would be rude to everyone involved. The first vector gets the easiest treatment. Rename it U1. Measure it. Divide by its length. Even linear algebra occasionally shows mercy. For the second vector, subtract its shadow along E1. The leftover is orthogonal to E1, which is the entire point, despite the notation trying to look intimidating. For the third vector, subtract both old shadows. What remains points in a brand new perpendicular direction. The algorithm has standards. So the original basis has been replaced by an orthonormal basis with the same span. The old basis was useful. This one has manners. Now the vectors are polynomials. And the inner product is an integral. Same Gram-Schmidt, just wearing a calculus hat. The first polynomial is 1. And it already has length 1 on the interval from 0 to 1. A rare moment of peace. To fix x, subtract its average value on the interval. Then normalize. Yes, this is literally centering a function before pretending it is civilized. For x squared, subtract the part pointing toward 1, and the part pointing toward the corrected x. Shadows again. Very repetitive. Very effective. The final normalization gives the third orthonormal polynomial. It looks designed by a committee, but at least it is correct. This is an orthonormal basis for quadratic polynomials on 0, 1 with the integral inner product. Same idea as R3. But now coordinates are hiding inside integrals. Delightful. In the way paperwork is delightful. Both examples followed the same script. Subtract old shadows. Normalize what remains. And keep the span unchanged. Gram-Schmidt is repetitive because correctness often is. Next, we use this orthonormal machinery to explain projection, where linear algebra finally starts doing useful geometry instead of just rearranging symbols for cardio.